Hello everybody, my name is Chris Klein and I'm the Global Product Manager for Q-TOF and iMobility. I'm really excited to talk to you today about our new solutions from screening to confirmation, a comprehensive food safety analysis from initial DIA screening to automatic reinjection for confirmation. And when we talk about workflows at Agilent, this typically comes together with a whole series of looking at the workflow from sample preparation to separation, detection, and final reporting. And all of those steps are going together with services and consulting with expertise as well as consumables and reagents. And the impact on that is it really adds value through integrating the technologies and services all together. In this talk today, I really want to, or in my first 10 minutes before I give it over to my colleague Kate Zimmermaker, who will really guide you through the application itself, but I want to highlight two new products introductions we are having, one on the separation side and one on the detection. So let me start off first with introducing the new 1260 Infinity 2 hybrid multisampler. So what this instrument makes so autosampler so exciting is we maintain our classic flow-through injection, and that allows us actually to minimize dispersion, and it behaves like all other autosamplers. But what is new is that we have now also a feed injection which injects the sample directly into the flow, and with that mediates strong solvents effect, and it's really a unique feature. So this is a new product introduction here at ASMS. And the way how it basically works is if I start off my sample prep, and this is typically done over Catches extract, where I have an extraction in very strong solvents, that the impact on that is I can get the analysis dispersion optimized, but on the other hand, I can get, particularly for polar compounds, a very poor peak shape. This can be minimized by using the new hybrid multisampler, which does not require a dilute and shoot sample prep. And with that, there's no breakthrough, a perfect peak shape, improved sensitivity, and peak integration. To give you some examples on this, my next slide shows basically the comparison of the Agilent feed injection mode at the top, the flow-through mode at the bottom, and at different concentration, 0.5 microliter to 2 microliter from left to right. And what we can see is that at very low injection volumes, the peak shape looks very similar, but going to higher injection volumes, it actually goes down, and it really shows the impact for very polar compounds using the feed injection. Again, both of them is possible on the same multisampler, and that allows for application to choose the one or the other mode. What really excites me as the Q-TOF product manager is also to introduce to you our next generation Q-TOF, and this is Reviden Q-TOF, and it's the most intelligent Q-TOF ever produced. And where comes the name from? This is Reviden, which means revolutionize your identification with rock-solid evidence. So that's on the name, and a lot of things have changed. First of all, if you really compare it in the layout, we see Reviden Q-TOF to the front, legacy instruments in the back. So it's an instrument which substantially looks different, but maintains the branding aspect to be recognized as an Agilent Q-TOF. There's a lot of things which have been improved over it. We have a new calibrant delivery system, which is based on piston pumps and delivers constant flow, internal reference mass, as well as calibrant. We have a new ion optics on it, using from the triple quads as a testimonial to our commitment to robustness. We have vac shield for the very fast removal of the capillary without venting the system. We have a temperature stabilized flight tube, which means maintaining mass accuracy. But what really most excites me is a new detector. For the first time in 15 years, we introduced a new detector, ultra-fast detector, which really gives us an outstanding dynamic range, and due to its perfect mass spectrometric peak shape, mass accuracy, which is really unprecedented. But going overall, this is really just the foundation when we talk about the hardware. We're delivering things like resolution, isotopic fidelity, mass accuracy, dynamic range, sensitivity, fast acquisition. But based on that, we are building workflows. For example, for the non-targeted and targeted workflows, the center column is instrument intelligence, the alignment with the LC triple quad, as well as the new web-based application, tune calibration and diagnostic. And what I mean with that is that for the non-targeted workflows, we have two new software, Mass Center Explorer for profiling and statistical analyses. We have ChemVista, which allows us now to access public third-party libraries. We have the Q-TOF screener on the other side for target suspect screening. And instrument intelligence, more on the next few slides on this, over new intelligent reflect workflows, which is basically an automatic reinjection based on the automatic data analyses, an alignment on the UI with triple quads, as well as, as said, the web-based application tune calibration diagnostic, which helps us do the most sophisticated troubleshooting on our new instrument. So when we talk about instrument intelligence, there are multiple aspects. The first of them is for sure the tuning. We implemented Swarm Tune a long time ago on Q-TOFs to really have application-based tunes. Is my molecule fragile? I have a different tune than if it's stable. If it's a small molecule, it's a different tune compared to a large one. All of them are completely optimized. I have the early maintenance feedback for the system monitoring, which is again a constant display of the status. How well is my instrument performing? How trustworthy are my answers I'm getting from this analysis? Schedule tune, a big thing again for Q-TOF, because typically a TOF tune as well as a quad tune can take its time. If I want to do multiple tunes for the lab, the best thing is to do it scheduled. And lastly, as mentioned, the reflex injection logic, which allows us to do an automatic re-injection. But first of all, how does it really look like? Everything at a glance with early maintenance feedback. So basically, from the status of my tune to some of the hardware components, I know immediately how good is my system, do I need to do something, or can I wait till next week to do it? So really a kind of a feedback of how urgent, how well-being is my instrument. The scheduled auto-tune, again, important aspect, it takes a long time, and this has a different time schedule. So for example, an overall Q-TOF systems tune, I might want to do on a monthly basis. If I think about different transmission application tunes, maybe bi-weekly or weekly, but what I sure want to do is to have my mass calibration, which is part of the check tune, but basically done on a daily basis. And that's the convenience of it. Rather coming in on a Monday and wasting half a day of tuning and calibration, let's schedule it, do it on a Friday night when typically the instrument is idle, come in the lab on Monday and be productive from the beginning. And talking about productivity, this is now the intelligent reflex workflows I mentioned before, where we have carryover, which means if a known contaminant is carried over to the next sample, we continue to do blanks instead and wait till the signal is below a threshold in a blank analysis. Above Cal curve, this is a situation when your sample has a very, very high responder. And what we can do now is to set up, for example, we have 1 microliter injections to do a 0.2 microliter. With that, we reduce the abundance by whatever response factor it is and have the ability to move it back into the concentration curve. And lastly, there's also fast screening. So I have, for example, a short LC gradient up front. If a compound I'm looking for is present, I basically switch to a longer gradient, and with the longer gradient, get all the benefits of the chromatography part. That's why it's fast screening. But we also have 2 new workflows for LC-Q-TOF, and those are the suspect confirmation, where Kate will talk more about it, as well as iterative MS-MS. Iterative MS-MS is a workflow which allows us to do the most thorough characterization of a sample by excluding all the precursors which has been chosen in an MS run in the subsequent one, and then so on, so forth, exclude more and more precursors. And with that, you basically dive deep into the low abundant compounds. But what's really exciting is suspect screening, because this is our focus here also of this morning's seminar. And the way how it works is that we do at the first level a data-independent injection. That can be all ions or Curie, quadrupole resolved all ions. And the question is now, do I have questionable compounds or identified compounds, and maybe I want to reanalyze them more? We do the processing automatically in the quant LC-Q-TOF screener, and depending on how the compounds are flagged, questionable or trusted, I might choose to have as optional a second step where I know my M/Z and the retention time of those compounds and do a second injection, which is now targeted MS-MS. And with that, I combine the benefits of a completely data-independent analysis with the selectivity of a data-dependent analysis by doing the second injection using targeted MS-MS mode. So again, this is something where Kate will tell far, far more about it. I go in my last couple of slides now a bit into the overall alignment between LC-Q-TOF and LC triple quad. Because in many instances, both instruments needs to be present in the labs, one more for the screening, the other one then more dedicated for quantitation. And in order to make life as easy as possible, we harmonized the user interface as much as possible. That basically here shown, DMRM mode looks pretty much the same as a new mode from the Q-TOF side, PRM, which stands for Parallel Reaction Monitoring. And in order to make life even easier, we made it to the situation that we can take our .m method on a thumb drive, on a network drive, take it off from a triple quad, and move it into the Q-TOF. So one of the tricks on here is to use some formula within the compound browser to basically translate a unit mass acquisition in MRM to an accurate mass acquisition on a Q-TOF. But this is, again, testimonial towards how close we really want to set all of our platforms at Agilent. And lastly, when we talk about instrument intelligence, it also has to do something with interaction. And this is the way how we do method development, where in many instances it can be a bit of challenging to say, what is really my boundary conditions? I want to have at least 12 data points over the chromatographic peak, but what should be my MS1 or MS2 spectra rate? And what helps is now the addition of having the ability to depend how many, for example, Q-rate bands I want to have, and have interactively display. If I change the acquisition rate here, my chromatographic peak will go down. And so I have an immediately feedback what the rates in MS1 and MS2 implement for my application. So this is a really nice symbolic here where we basically can say, yeah, okay, less than a quarter of the time we spend on the MS1 domain, which we use for quantitation, and the MS2 domain, which are the qualifiers. Or I can also use a different display. Instead of a pie chart, I can use a bar chart. And the bar chart now allows me to implement multiple collision energies, including the display of it, and again, have the same display and optimize the duty cycle. So this is what data-independent analysis should be, a very easy, intuitive way to focus on a data-independent setup and then perform your later steps. With that, I reached the end of my short introduction about what's new at Agilent, our system intelligence, and hand it over now to Kate Zimmermaker to really go into the applications. Thank you.
Hello, and thank you so much for that introduction, Chris. I'm excited to talk to you all today about some of the data that we've acquired on Revident, the new LC Q-TOF. I'm going to work through some of our screening workflow, as well as the introduction to the intelligent reflex option. Through that, it's really important that we are using real-life samples to do this. So I'm going to show you some of the sample preparation, the all-ions data-independent acquisition for our screening method, the MassHunter Quant12 and LC Screener tool data analysis, and the workflow integration of a demonstration of intelligent reflex. The sample preparation is really straightforward and can be modified to whatever matrix that you're looking for. We started with organic broccoli, which was homogenized after being frozen. This was then measured to 10 grams in a conical tube and shaken with ACN. A Ketcher's extract pouch, specifically for pigmented fruits and vegetables, was then used, followed by SPE extraction and transfer to a secondary vial for storage and preparation for injection. Our analysis was completed on the 1290 Infinity 2 LC, and here are our LC conditions. We used an analytical column that was the Zorbax Eclipse Plus C18, and it was preceded by the guard column, which was all contained in our temperature-controlled multi-column thermostat. It was held at 45 degrees Celsius. The injection volume was 3 microliters, and the autosampler was kept at 4 degrees Celsius. Our buffers were acetonitrile and water with ammonium formate and ammonium fluoride, and we had a 20-minute gradient with a 4-minute post time. Using this particular chromatography, we got good spread of our retention times of all of the analytes that we were looking for, and we were happy to move forward with the analysis of our over 200 pesticide complex matrix mixture. Here are the source conditions for the data-independent acquisition using all ions. we acquired in both positive and negative mode. If you're unfamiliar with all ions, it is an independent mode of acquisition where we use an MS only, and we include 3 different collision energies. For our experiment, we use 20, 0, and 40. And this is beneficial because we get fragment information for all of the pieces of our mixture and all of our different compounds, whether they be targets or suspects. This experiment is certainly not limited to the collision energies that we've included, and it's also not limiting on the quantitative analysis software side, where you can go in and make modifications to do any different collision energies that you need, specific to the compounds that you're looking at. So what does my data look like with all ions? In the 0 collision energy, we see our molecular ion is our most prominent ion here. And you can see the other fragments that we're tracking for this particular compound are not showing up as much. When we add collision energy 20, those fragment ions start to come up. And then the addition of 40 collision energy, we've lost our molecular ion, but we have all of that additional fragment information. So the caveat here is that you really need to be working off of a library PCDL. And the optimization and curation of that library further can help in the identification of these different compounds. To build a library for our analysis, we leveraged ChemVista, the new compound library management platform. This streamlines unknown ID workflows, includes extensive curated libraries and databases for food safety, environmental, E&L, as well as forensics and toxicology. This allows for efficient library management with the ability to import multiple different file formats. Simply, your data analysis benefits from having a more curated PCDL, and you're able to do this using ChemVista by bringing in information from public libraries. Additionally, for all of our data analysis, we used SureMass, a low-level data processing algorithm that's designed to extract maximum information from our accurate mass data. Here, the profile data is converted into ridges and features that make up objects of interest. This is going to reduce file size, increase processing speed, while maintaining great mass accuracies and managing possible saturation that you might see in centroid data. We use MassHunter Quant 12 and the LC screener tool embedded in it for our data analysis. On the left, you can see our quantitation. The quantitation part is optional. You do not actually have to have calibration curve information to use this software, which is really great because this screening software can be used with anything you might be looking for. The screener tool is on the right, and I'll dig into both of these a little bit more. But the cool thing is these work in collaboration with each other. So as you move through one, you're able to navigate through the other. So all of the information that you're looking for is there and easy to find. So here is our quant interface. This is our batch view. We can easily see our chromatograms on the bottom left, including our molecular ion and our overlapping fragments with the clear ratio and coelution scores labeled right next to it, and the calibration curves as well. What's really great is that you can very easily toggle this manual integration aspect and make modifications or look in further to your overlapping fragments as well as your chromatograms. So experimental setup. We used organic broccoli extract in ACN and spiked it with 4 heavy labeled internal standards, as well as a 200 plus pesticide calibration curve from 0.625 ppb to 100 ppb. We used all ions acquisition, and we did 6 replicate injections in order to show reproducibility of our measurements. Here on the left, you can see how we go about setting up that LC screener tool. During our data analysis, we used SANTE guideline specifications in order to look at specific mass accuracy, signal to noise, or number of verified ions. All of that can be controlled on the left down here, and this is used to build what you see on the right. So you set the specifications on the left that you need and you want to see so that you can get and set the rigor that you need on the right for your screening analysis. This screen on the right can be set up on a by compound or a by group basis, making it very easy to import your targets and your suspects and set different specifications for either of those. Here's a little zoom in further on the LC screener tool. We see a simple traffic light designation, green as identified, orange as questionable, and red as not identified. This makes it really easy for an analyst to look at this interface and know what's happening in their sample right away. On the top left, we have our filter list, so anything in this list can be filtered by exactly what you want to see, whether it's a specific status or if it's a target versus a suspect. Further on the right, all of your samples, which are navigated here, are summarized on the top right with those different indicators. So this allows for really easy navigation and review. On the bottom, we have our different spectra. We can start on the top right of the bottom spectra and look at the experimental isotopes as well as the predicted boxes. And then with our all ions data, we get to see that 0, 20, and 40 collision energy very clearly right in front of our eyes. This makes it really easy for us to ever see if something is falling out of specification or if it's being caught as questionable. We can very easily navigate to the one that is that orange color and see exactly why that might be as a product of those different collision energy spectra. So let's look at some data. Our mass accuracy data can be seen here for our 4 internal standards that we spiked our compound matrix with. We can see that we fall well inside of that 5 ppm window that's required for Santee guidelines, but really great that what we're seeing is we are consistent in that 2 ppm window as well. But this isn't just limited to the internal standards that are held at the same concentration over the course. Here we have 25 different compounds pulled out with concentrations from our lowest calibrator to our highest calibrator, 0.6 to 5 ppb to 100 ppb. All of these 25 compounds are within that 5 ppm window and most within that 2 ppm window. This is also occurring over the course of 20-ish hours and without any work list stops or recalibrations. This stability comes through in our RSDs as well. Here you can see the majority of our compounds are well below the 20%, with the blue being our lowest, one of our lowest calibrators that we have, and almost all of them under 10%. The profile of how that is actually set up can be seen clearer here, with the blue as our lower calibrator and the dark blue as our highest calibrator. And the consistency of those 6 replicate injections can also be shown here with our overlaid EICs. A really great way to review dense Q-TOF data can be found in our quant software. We have the ability to use compounds at a glance, which can be shown here. This lets you do manual integration and to look at all of your compounds as you're going through. And we have calibration curve at a glance, which is fast and customizable, easy to look at, and get all of your information for all of the compounds that you're interested in. But you don't have to click through all of these on your own. We also have auto review samples that will make that happen for you as you go through and pulls it in front of your screen as you go. So on the quant analysis side, we can see our detailed chromatograms, fragments, and calibration curves. With Mass Hunter Quant, the data is shown had great linearity, with the majority of compounds being over 0.99 R² value. And that can also be shown here as far as how you can very easily see your molecular ion chromatogram and then your fragments right next to it. So this is an example of a compound that you would see from our absolutely lowest calibrator to our highest calibrator. And part of this is the benefit of bringing multiple fragment ions into your quant analysis as you're looking at different compounds. This can also help to optimize that method however you like to look at your data review. So although we see some of those fragments in the noise for our lowest calibrator, we can see that everything that we've included in the 6 is available for our highest calibrator. And we're able to rely on our screener tool results and the number of verified ions to do that for us so that we don't have to dig through that. But if you want to see the selective fragment ion, it's very easy to set that up so that as you're reviewing, you can see a very clear peak in fragment coelution. So of course, there will be coeluting isomers. There are different strategies for managing those coeluting isomers. Here you can see these two in particular are showing up as actually the same peak via our screener tool. So something that you can do very easily is to go in so that a reviewer would always be prompted to review that by making the compound name both names. Another way to do that is to make it more selective. So because I brought all of those fragment ions in, I was able to find the one that was most specific to each of those. The problem here is because we're still using the same quantifier ion, we have those both show up as orange. Another good way to prompt a reviewer for review, but there is an alternative option. By swapping the qualifier and the quantifier ions, we make it a more selective data analysis method in our screener tool, and we're able to get those separated, both confirmed as identified, and see that we're getting 2 of the separate peaks. I talked about how it's important for us to build our analysis off of curated libraries, but that's not always the case. We don't always have that information, or it's not always openly available for us to move into our PCDL. So we wanted to run an experiment to see what the results of getting rid of some of that information would be. So we used 120 different compounds and designated 30 of each of them to different PCDL information states. And I'll go through that here. So on the first, we have spectra and retention time for both of those. And we were able to get 30 confirmed identifications via the LC screener tool. When we had the spectra, but we lost our retention time, we did have to modify our criteria to greatest response. And we made that a wide retention time window for those fragments, but we were still able to get the full 30 that we had modified to that different PCDL information state. When we had retention time and no spectra, we were able to keep that window small, but we needed to change our criteria to close retention time and also change to a verified ion of 1 because we didn't have that fragment information. For 4, we have no spectra and no retention time, and we changed to greatest response, verified ions is to 1, and we really are relying on our mass match score for making this particular identification. So what is mass match score? Mass match score is a weighted aggregate of mass accuracy, mass abundance, which is isotope distribution, and mass spacing, or isotope spacing. And all of that is combined to give you a good identificative score for your analysis. This is what our LC screener tool results looked like for all of our different calibration levels. We can see calibrator 1 at 0.625 to 8 at 100. What's really nice is that we don't see much of a difference between 5 and 100, but we do want to manage what we're going to do with these questionable compounds here. This is where the new intelligent reflex workflow could really shine in helping to give you better answers, but also reducing the time that it takes to get those answers. So a traditional screening and reinjection workflow can be seen here. It includes lots of different steps, as well as a large instrument idle time while you're making those decisions about reinjection. The intelligent reflex reinjection, which Chris started to give you information on at the beginning of this talk, allows us to use those screener tool results so that we can automatically re-inject questionable or identified compounds, so that when we come back, we have the answers as to whether those are identified or not. And what that does is it not only takes down the time that it takes for me to make those analysis choices, but it also keeps the instrument running and having real injections go through at a quicker pace. And what is the benefit of target analysis, and why are we able to make better identifications with that targeted analysis? It's really the noise that comes through on the all ions. So when you're doing that data-independent acquisition or screening, you're getting fragment information for everything. So lots of things are popping up. On the right, you can see for this particular compound, the fragment spectra that we were able to get from our library. And we went in and I wanted to highlight some of those different fragment ions that we were looking for. You can tell in the targeted MSMS compared to that of the all ions, those are so much more abundantly clear from the rest of the ions that are available. So here is just a general look of what that screener tool could look like with that targeted reinjection. Targeted MSMS can also be used with the LC screener tool. It's not limited to a data-independent acquisition by any means. And what was really neat is that for a sample screen, we identified 182 of our 254 compounds in our PCDL. 22 of those were questionable and 50 not identified. Upon targeted reinjection, we were able to get identification of 18 of those 22, which is over 80% identified from our questionable list. So what did we go over today? Chris introduced the new Revident LC Q-TOF and the new hybrid multi-sampler. I showed you some catcher's sample preparation for our organic broccoli matrix and talked about our all-ion screening of 200 plus pesticides in both negative and positive ion modes with good mass accuracies, low RSDs, and very linear curves. And the use of Mass Hunter 12, Quant 12 for suspect and target evaluation, as well as the use of the LC screener tool. Following that, we went into the intelligent reflex workflow and a demonstration of how targeted MS reinjections can benefit the overall identificative workflow on the screening side. I did want to put this next slide up. Lots of people helped with this outside of just Chris and I want to acknowledge their efforts as well. I really appreciate your time and would be happy to answer any questions.
Well, thank you both for your excellent presentations. We now have time for your questions. So our first question is for Kate. How do you improve the recovery percentage in fruit, vegetables, water and soil using the catcher's sample prep method analysed by LC-MSMS?
Yeah, that's a really good question. I think there are a lot of points of optimization that can happen on the sample preparation side, specifically with catchers, and lots of ways to improve that recovery. Some of those are going to be specific to the matrix for the problem that's actually presented. First, you want to make sure that everything that you're using is up to date and of the right quality for your reagents. And then when you get into that actual sample preparation, there are some limitations as far as what sample you should be using. If you're under 25% moisture level, that's when it might be beneficial to add water in order to enhance the recovery. Sometimes that happens with dry soils. Another piece is the addition of ceramic homogenizers. So everyone shakes differently when they're doing the sample prep. If you're doing it by hand and making that consistent can be really helpful, but adding those homogenizers can also continue to break that up and make it more consistent among different users. And then when you're adding those salt packets, it's important to add the packets to the mixture itself as opposed to adding the mixture to the packet. That can help with some of the thermal event that happens. And there's been some studies on recovery done for particular compounds where that thermal event can have a big effect.
That's great. Thank you, Kate. We have another question for you. How do you screen and quantify for residual pesticides in fruit and vegetables?
Yeah, so as we saw in the presentation, there are a lot of ways that you can do that simultaneously. So you can screen and quantify at the same time. In our particular example, we used an all ions method of acquisition. And this is in order to give us that fragmentation, but also getting all of our ion information through. There's another way that you can do this succinctly with quadruple resolved all ions or Q-ray, which we went over just briefly in the presentation as well. This is where you're using that broadband isolation. But on the beyond the acquisition and onto the data analysis side, we're really leveraging our Mass Hunter Quant and embedded LC screener tool software. That allows us to do that quantitation while we're doing the screening all together and get confident identifications along with the quant data.
Thank you. Thanks, Kate. So yeah, we have another question for you. Do you have any tips about LCMS?
Yeah, I think that's a broad question. I think in general, when you're setting up a new method, be really considerate of all of the locations of your flow path. It starts from the LC and it ends at the mass spec. It's really good to create a method development process that you can walk through and be consistent from application to application. And then additionally, just regular care and maintenance for your mass spec and your LC can be really helpful in making sure everything is up and running and ready to go. Regular tuning, scheduling those tunes and those calibrations, as well as just making sure your LC is fleshed out between applications, day to day. It's really good to just stay up on those different tasks to make sure everything's up and running.
That's great, thank you. So another question for you, Kate. What are the best practices for sample preparation in the context of screening and confirmation?
Yeah, so when we go back to that first question with the sample preparation using catchers, there's more ways that we can enhance that even further. There's been some studies where users have engaged EMR lipid cartridges to clean that sample up even more. The best practices are likely going to be due to whatever matrix you're using, how dirty it is, what you need to get out of it. So experimenting within the limits that you are able to experiment within those regulations and adding some of those things like EMR lipid extraction can be really helpful.
That's great, thank you. So a question now for you, Chris. What is shore mass in Q-TOF and how can I use it to my advantage?
Very good question. So as Kate also briefly described in her presentation part, it is a method where we distinguish finding features based on profile data. And this is very important to notice because most algorithms are running on Centroid data, and with that, don't really have the sensitivity that many applications demand. So using the shore mass algorithm helps us to really detect the features based on the profile data, and it also minimizes any effects based on peak saturation, and with that, the mass accuracy will maintain basically like the same for non-saturated samples. This is really the main benefit that shore mass gives us a sensitivity that normally only profile mode would allow.
Thanks, Chris. We'll go back to Kate now for the next question. Can you provide more information on NTS screening?
Yeah, so when we're doing a non-targeted screening, we're not creating any isolation that would stop us from getting information from other ions. So we're not just targeting one particular thing. We are able to do that through some of those acquisition modes that I've already talked about, like all ions, or Q-ray, where we're using that broadband isolation. So we're cleaning it up without really removing things. A real benefit to working in an untargeted fashion is the ability to look at samples retroactively. So because we're not doing that isolation or removing anything, we get a lot of information out of that. We can go about this in a targeted manner when we're doing data analysis, but if later on we find something that we want to go back and look for, a new emerging compound, then we're able to take that and look at that same untargeted data in that targeted fashion for that particular compound. And this can be really helpful because you don't have to reacquire something that might have gone away. You can simply pull that data file back up, use the Mass Hunter Quant or some of the other, whatever data analysis platform you prefer, and add that in and do a search through that same data file.
That's great. Thanks, Kate. We'll go back to Chris now. Do you have any collaboration opportunities?
Oh yeah, absolutely. I mean, this is really one of the aspects to say the best products are really based on direct interaction with customers to really address the needs of today and tomorrow. So if there are any interest to work with Agilent, please contact either your local Agilent service representative, or you can also reach out to me directly.
That's fantastic. Thank you, Chris. And the next question is for you also. How difficult is it to tune the MS instrument?
Great question, because this is really the biggest effort we put into the development of the control software to make the tuning as easy as possible. And there are multiple levels of the easiness. The first of it is that we combine the quadrupole and the TOF tune, and with that minimize a lot of typical errors we have seen in the field. The second one is we also further selected groups tunes based on the application context. So a lab manager can basically now select given number of tunes that are typically used in the lab, and then over roles and permissions, those tunes will only be visible, for example, to the technician by pre-selected from the lab manager. And third, and this is really something where Kate already mentioned on it, is the ability to do scheduled tunes, because tune, particularly on Q-TOF, will take its time. And so having the ability to tune the instrument basically on automatically on Sunday afternoon or Saturday night and come to the lab on Monday morning, and the instrument is freshly tuned and calibrated, this is a huge time saver. And expanding a bit on that, we basically also have the ability not only to tune the instrument over scheduled tunes, but also to calibrate. So for example, we can say, yeah, every month, give myself a systems tune where everything is basically tuned from scratch. But if I decide to go for the best mass accuracy, I can schedule something for every morning, 4 a.m., and have my instrument ready to set up on the work lists. So that's, again, all on the impact of making the lab as efficient as possible and by minimizing human error as much as possible.
That's great. Thanks, Chris. So another one for you. How can you upload a unit mass TQ method to an accurate mass Q-TOF method?
Okay, there are multiple steps on it. The first one is we can directly upload the .m method from a triple quad to a Q-TOF. So Agilent system operate on Mass Hunter, and it's the same core principle between triple quad and Q-TOF. All the source conditions, everything will be taken. All the LC conditions will migrate immediately. So the main aspect is now how to move the actual compounds over. And this is done over the compound browser. The compound browser is a tool typically developed on triple quads, but we utilize that utility in Q-TOF to basically upload all the individual transitions into a new acquisition mode, PRM, parallel reaction monitoring. With that, the user has now the ability to select, to collapse either all the transition into a single MS2 file, or to optimize the individual transitions for interferences. So the other trick we are using is if a customer adds the sum formula of their compounds, we immediately can correct the unit mass of the precursor to a high resolution accurate mass on the Q-TOFs. So those is the basic principle, a combination out of the compound browser, the direct ability of using the same platform, as well as the ability to deal with the transitions individually.
That's great. Thanks, Chris. So another question that we've received is, what is AI-based tuning?
Maybe I address this question. So AI-based is, in its simplest definition, a decision that a machine or instrument is doing. And for the tune aspects, we historically always were working with our most experienced experts to get the maximum resolution tune out of it. But the human mind and the way how computers work is a human can only do one step at a time. And this is the biggest difference, that with our AI-based tuning, we tune multiple elements together. So if I look at the overall TOF instrument, I have multiple elements which decide how my ion beam is getting into the time of flight, which operations needs to be done on the mirror. And all of those are 3 to 4 different elements, all impacting the resolution. And what the AI-based tune is doing is now not only doing a kind of a pre-ramp function, but also having the ability to tune 4 elements simultaneously together, and with that really achieve the absolute best maximum. And by implementation of this, we figured out that basically the algorithm is so efficient that our most experienced tuner in R&D basically does not achieve the same good results that our tune does. And that was really a very great accomplishment.
Oh, that's great. Thank you, Chris. So we'll go back to you now, Kate. How difficult is it to add new analytes of interest to your analysis?
Yeah, that's a good question. And it kind of goes back to the retroactive analysis. There's times that you're going to look at these samples and these data files on the first pass and realize that you want to add something else, whether it's something that you just forgot to add, or something that's emerging and something you need to add. It is as simple as a button. You can either create a new compound within the method by right-clicking in the method editor and adding that value in, or if you do have a standard and you're able to collect spectra for that, you can load that spectra in that you've taken, or you can go and search into ChemVista, our new library management software, where there might already be spectra for this compound, and pull that into your PCDL, and that can be loaded with a single click into your method. So it's very simple, and there's lots of different ways to do it based on whether you need to collect that spectra or somebody else already has and it's available in your library.
That's great. Thank you, Kate. And we have one final question for you again, Kate. How are intelligent reinjection results reported out?
Yeah, so with Revident, it's a huge value add to be able to have this targeted reinjection screening. But if you have all those data files and you don't have any way to look at them really quickly, it can become a lot of data. Agilent has a report format that actually combines your all ions or your untargeted acquisition results through Screener and your targeted acquisition results through Screener. And what's really nice is those are all lined up, and the view is very similar to what you would be seeing in our batch at a glance as available on Mass Hunter Quant. So as far as the quick eye recognition of the results that you're seeing there, it's very easy, and all of that is in a single report. So you have your all ions that gets acquired, you trigger your targeted reinjection to go, and that is appended to your work list. And at the end of that, you have all of those individual data files, which you can go in and interrogate, but you also have this really nice, succinct report that summarizes all of those different pieces.
Well, that sounds perfect. Well, I think we'll wrap it up there. Thank you again to both of you. And if any other questions do come in, I'm sure that Kate or Chris will be happy to respond to them via email.